All right. So Traceroute. What's the tool used for?
Basically takes the path. Well, if we want to use the mail example, it's like the way that your mail is traveling when it gets to the final destination.
Okay. So it shows you all the hops it has to go
Sends you
through.
back messages. Hey, I made it here. I made it here now.
Okay, so it shows you all the hops along with the time to each hop that it took to get from your starting point to your destination. So you can kind of see if you're going to www.google.com, what are all the hops you have to make to leave campus here to get to google.com through the internet, which is a network of networks. Okay, why do we need it? What's the advantage, or what things can you do with Traceroute? Go ahead.
It minimizes data loss. I mean, you can minimize data loss and increase speed with it because you know exactly where you lost. Like, you'll know exactly where you lost a packet or something like that.
Okay, so if you're having network problems,
Yeah.
for instance, if you can't connect to google.com, you could use a traceroute to try to determine where the problem is.
Yeah.
The problem could be at one of the hops in the middle that's blocking you. That makes sense? So if that's the case, depending on who has control over that hop. So for instance, let's say that the problem connecting to Google from here on campus might be the very first router that Concordia's router connects to off campus. Let's just say that's the dead one. Well, Concordia can roll over to a different first hop leaving campus by probably failing over to their secondary DNS, which is going to have a different first jump that might clear the path then. So the idea if the first place is broken. Otherwise, whoever did the trace route would have to then go and communicate with the people who are running that machine and say your machine's not forwarding packets correctly, that kind of thing. So you're seeing the whole connection. So you can see where your connection's breaking down. Okay, so last time we were talking about some possibilities for the network core, kind of how the network is built. How the interstates are used in a common network. So the one we started talking about was this idea of a packet switched network, where we chop up data, the data we're sending on the network, into little tiny pieces, stuff them into an envelope called a packet, and that packet's going to have some sort of fixed size depending on, the magical roll of a dice for what we think is the most ideal thing for performance and accuracy on a network. And we're going to send the stuff along the network in packets, and hopefully nothing more than one packet gets destroyed. We talked a little bit last time about what the size of those packets should be. You probably are not going to put one bit of data inside of an envelope and send it. The example we were using last class is about if you were sending a book. You could send it one page at a time. 500-page book would take 500 packets, 500 envelopes. Maybe you send it 10 pages at a time, less packets, but if one gets lost, you lost 10 pages. You've got to resend 10 pages. So somewhere in there, there's that balance. We talked a little bit about store and forward. So this is all kind of alluding to this idea of having some sort of global protocol that we call TCP/IP that guarantees our data will arrive at the endpoint eventually. Okay, that's the job of TCP/IP. But before we actually put a name to it, I've just kind of told you the name, but before we put a name to it, we think about this idea of maybe a store and forward type of network where at each hop along the way, like we were talking about with this trace route, or at some designated hops, that network takes the packet and makes a copy of it and keeps a local copy. The advantage of this, if we assume at some point in the future there's going to be a protocol that's going to allow us to resend data automatically in the event that it didn't arrive, not having to go all the way back to the very beginning is advantageous. If we could have one of the hops in the middle retransmit a corrupted packet because it stored it before it sent it. That makes sense? The cost of that, though, is the time it takes to store it. So it's going to grab it, it's going to copy it, and then it's going to send it forward. Now, if you were to do a trace route, you'd see the time is usually in milliseconds. Typically, the different hops, the ones that take longer, are probably store and forward routers. So that router has a designated amount of memory on it that it's using for storing packets before it sends them. You can kind of think ahead a little bit and decide, okay, well, how long does it store a packet for before it just decides this is no longer necessary? At some point, there needs to be some sort of message set letting you know that, okay, the packet that you had stored did arrive successfully. You no longer have to store it. Who might that arrive from? So let's say that you're sending data and there's 10 hops between the source and the destination. You're hop number 3, so you stored the packet. You store it and then forward it. You're forwarding the packet on to hop number 4. When hop number 4 receives that packet, if he's a storing network, if he stores that, or he's a storing device, if he stores that packet successfully and then forwards it, can't he then let you know that he successfully stored it and you're now wasting your time? You no longer have to hold on to it, right? Because the guy in front of you successfully received it. Okay, so this kind of goes back to this idea of a network of networks. You're only protecting the packet so that it arrives at whoever you're sending it to. And only if he doesn't store it, do you still need to hold on to it. Does that make sense? All you're trying to do in our foreshadowed store and forward network is you're trying to guarantee that you've done your job. That means you've gotten the packet from you to whatever your direct destination is. Make sense? Okay, so store and forward, all this crap down here is just talking about the delays associated with store and forward. We're having to do some extra crap, it takes some extra time. Fair enough. Let's see. So, more delay stuff. Keep in mind that when you have a router, so this just adds kind of a second layer of delay. Here, we might have been thinking that when a router receives a packet, it just immediately stores it and sends it on. So the amount of time we have to wait is only the amount of time it takes to store the packet. Well, now we have another layer. Do you think that that router's only job right now at any point in time is the one packet that's coming through it? Or is it probably handling a lot of internet traffic at the same time? Well, so there's got to be a line, some sort of queue for that. And now this kind of gets back to almost an operating systems discussion. If you are a router, which is likely the piece of equipment that's going to be storing and forwarding, because routers do that, they receive data and route it on to another place. If you're a router and your job is to store packets and then forward that packet on, how do you do your storing? What are some options for us to store data in computers? It's not a trick question. Hard drives?
Yeah, you can store on the hard drive.
Okay, so we can store crap on hard drives, right? Okay, now a router, those of you who have like a home router, like one of the Wi-Fi things or something like that, that's not a general purpose computer, is it? You could have a general purpose computer. You could set up your Mac or your PC to act as a router if you'd like. But typically when we think about routers, even for the ones we buy at Best Buy for consumer use in our homes, it's a dedicated piece of equipment that was built specifically for doing routing stuff, right? Now, do those things usually have hard drives in them? So Best Buy, you sell probably, let's talk about like the Linksys line of things, which is a Cisco product. You probably have 3 or 4 different levels of Linksys Wi-Fi routers, right?
Yeah, we do the Linksys AC1200, the Linksys AC1900 Plus, and the Linksys AC2100. And those are the only decent ones.
Okay, and the only difference is price, right? They're identical otherwise?
Range. And
Okay.
One's an N band, or one's not an AC, one's an N band.
Okay, so part of it's technology, the radio technology. Some of them also is range of them, so they have more powerful transmitters on them. Do any of them? Even the most expensive ones. I'm guessing the most expensive one's probably in the high ones, 180, something like that.
Well, the most expensive one we have is like the Nighthawk, and it's about $300.
Okay, well, out of Linksys.
Out of Linksys, yeah, I think 180.
Okay.
Maxed out.
So that one doesn't have a hard drive, does it? Do any of them have hard drives?
No.
No, none of them have hard drives.
Unless you go for max size, then you got the airport express or the airport time capsule.
Yeah, but that's actually 2 products in one,
Yeah.
right? That's a network storage device, and it's a router, not necessarily related to each other. Okay, so the punchline here is that that piece of equipment doesn't have a hard drive in it.
It does.
Now, it's that one does. I'm
The
saying
Linksys
the
ones actually do have a
USB port, so
Well, no, they have a processor in them and RAM though, so data can be
Okay.
stored in RAM.
Okay.
They do have the smart function.
all right, so talking about different ways of storing stuff, if we had a router with a hard drive in it, is that a good solution for storing packets as it's flying across the internet?
If it was solid state, maybe.
Even solid state. What's if we were talking about the good parts of hard drives? What's good about a hard drive?
Are you talking about
Store
network
for
area?
percent.
Huh?
Are you talking about NAS devices like network area storage?
No, we're talking about routers and how they do store and forwarding. So just hard drives in general.
Store a lot of stuff.
A lot of stuff. They hold lots of stuff at the cost of what?
Speed.
Speed. They're slower. Okay? Even our solid state drives are still painfully slow in comparison to other mechanisms for storing stuff, right? Okay? The worst case scenario for if we were storing this stuff on a hard drive, I mean, we kind of just used the example a few minutes ago that this isn't the only packet that this guy's trying to store at this point in time. You have this queue, a bunch of people, a bunch of packets waiting in line to get stored by a router before that router forwards that packet on. And this probably isn't like 5 packets. It's probably more like 5 million packets, right? Lots of them. Well, specifically mechanical hard drives, so hard drives actually have a spinning magnetic disk. I mean, those things are going to break down if they're having to store that much stuff, right? You're going to spin to one spot, write it. Spin to another spot, write it. Spin to another spot, write it. You're going to have mechanical failures on top of it being slow. Probably not going to be acceptable. What about RAM? A lot faster than memory? Or a lot faster than hard drives? Sure. Is RAM big enough to store a lot of packets? Potentially. Potentially. One thing you might notice if you look at entry-level routing equipment versus professional-level routing equipment is the amount of onboard RAM, the amount of memory it comes with. Typically, the memory in professional quality isn't the equivalent of like our RAM sticks that we put into our computers. It's actually a faster type of memory than even that. Because you're paying a premium, you want them to be fast. You don't want your slowdown to be drastic for the time it takes to store a packet. That makes sense? So these small little Linksys routers that are used for consumers, for your home, how much memory do they need to have in it to do their job? How many computers are likely attached to a consumer level router in your home? So use your
5 devices max.
5, 6, 7, not a ridiculous number of machines, right? Okay, and out of those, how many are sending information simultaneously? At most, all of them. So at most, 7 or 8, 9, 10, whatever, something like that. And how big is a packet? I mean, we're not talking about the details of the algorithm at this point, but probably not big, relatively speaking. So they could probably put, 3 megabytes, 4 megabytes of fast memory in there, and it could probably keep up with your small local network in your house. Not a huge amount of memory is the point. That's part of what keeps the cost down. Now let's think about the router that we use, the edge router here at Concordia. How many machines are on that network? A lot more,
Apparently too many.
right? A lot more machines. Okay, would 2 or 3 megabytes of memory cut it? Probably not, especially when you have a higher likelihood of more people being on at the same time. So in your house, if you have 10 devices, realistically speaking, maybe 3 or 4 of them are doing something at once. It's not an unreasonable statement, right? Are there more than 3 or 4 machines doing something on campus at the same time?
I hope so.
There are more than 3 or 4 machines in this room doing stuff at the same time right now? Sure. So it's solving a much more difficult problem. Many, many, many times more difficult. So it needs more memory to store that stuff. And it probably then needs faster memory because the queues, the lines waiting to store a packet before it gets forwarded, are also longer. Make sense? Okay, so the benefits of store and forward is to support resending of data so that it has to travel the least distance when it gets resent as possible at the cost of speed. But
I was just gonna ask, with memory, I know like hard drives, you can store one thing at a time. With memory, is that the same? You can store one thing at a time, or do they have something where you can store multiple things at a time?
well, you could store multiple things at a time if you have multiple banks of memory. So a lot of times, at least the professional level equipment they would have, they might set it up where, I mean, these things are very expensive. So you're almost dealing with memory speeds that are similar to like CPU registers or L1, L2 cache, something very close to the CPU. And what they do is they have several banks of them wired into a hardware queue. So what happens is, let's just use an example of 4. So you could store 4 things simultaneously, and as long as the processor that's actually taking these things and say, okay, it's time to store you, it's time to store you, as long as that guy can keep up, it's almost like there's no delay or a minimal delay. But on our Linksys $40 router you get from Best Buy or something, it's going to have not a very fast processor in it, a relatively slow amount of memory, but it's only having to support your local machines. Well, there's nothing wrong with Best Buy. I have a Linksys router in my house.
I know. It fell off the wall.
Yeah, but I mean, do you want to spend $15,000 on a router for your apartment,
No,
or do you want to spend $40 for a router in your apartment?
I'll drop $200 on an Airport Extreme though.
Why?
Better quality.
Is it?
Yeah.
I bet you almost anything is the same parts in there. Anybody important? Oh, California.
Oh, I'd have to say probably the
More than likely, the Airport Extreme is probably using similar radio technology to the higher end Linksys. We're not talking about night and day type stuff.
You're talking about $40 one.
Well, fine. So Apple doesn't really make a $40 one. You know. But bottom line is, it's just like the laptops and their desktops. It's the same hardware in them. They put a nice little Apple logo and they make it work really well with their stuff. So, for instance, if you have a lot of Mac computers, getting an Airport Extreme might make plenty of sense, or a time capsule, which has the hard drive, because it works really, really well with just your equipment. You could just go on there and find the time capsule. Well, if you're using a PC, it doesn't work as seamlessly. They probably only did bare minimum amount of testing, and they said, well, PC users don't like us. Maybe it'll be their gateway drug to go buy a Mac or something like that. Okay. So more money spent on a router will not necessarily give you a better experience, is the punchline. Things that you're getting with a more expensive router is faster maximum speed, but even that you might not have a realized use. So for instance, if you are at your apartment and you have a router and you're mostly using a router just to connect a whole bunch of devices through Wi-Fi to the internet, and your internet connection is 30 megabits per second, you don't need a wireless N router. That's more than you need. 802.11g is plenty. It's 54 megabits per second. That's faster than your internet connection. All of your machines will be able to maximize it, assuming they can get a download speed from whoever they're downloading from, or an upload speed from whoever they're downloading from, to maximize their 30 megabit connection. Well, if you're sharing a lot of data between multiple machines on your network, so if we're all on the same network and I'm sending a file from here to here, now we're no longer using our internet bandwidth. Now we're using our wireless network bandwidth. In that case, one of the newer technologies that has a lot more bandwidth, they use a broader spectrum for sending the data, would be better, because we can send our data more quickly. If I'm trying to transfer a large file at 100 megabits per second versus that same large file at a gigabit per second, it's going to go 10 times faster. Make sense? Okay, so it really comes down to how you're going to use your network. Most people are not using their network at their house for sharing stuff internally on the network, outside of maybe like a printer, right? That's kind of a common thing. You might have a network shared printer in your house. so everybody can print to it. But outside of that, it's not really commonplace for people to have like a server set up in their house for sending stuff. Maybe you're copying a file between two machines, but if it's like a Word document, not going to really notice the speed difference between a 100 megabit and a 1 gigabit connection. They're both just going to kind of copy instantly. It's just going to happen fast. So it's an important thing to know that you don't have to go and spend more money to get a better router, because you're going to have all this technology sitting there that you can't use. Make sense? So, in any case, the more expensive routers you buy for commercial enterprise type use are going to have more memory, faster memory. Typically at the enterprise level, you would not have one machine that does both wireless and wired routing. You would have, that's kind of a enterprise level wireless router. That guy up there, okay, that's not for a wired network. That's just an access point, a wireless access point that's plugged into a wired router somewhere. But for our little home networks, those Linksys are really, I mean, they're nice. 30 or 40 bucks, we can do all sorts of stuff, right? Okay, so two places where we lose speed. One is the time it takes to actually store the packet. The other one is waiting in line while we're waiting for the time it takes to store the packet. So we got to play this balancing act. Okay, core functions, routing, determines source destination, route taken by packets, so that we're going to talk about specific routing algorithms. So for instance, when you perform a trace route, we type in www.google.com from here, it's going to show us the 6 or 7 hops it takes to get to Google's server. Somebody had to dictate where the next hop was, and that deals with routing algorithms. So each router is running an algorithm. It decides based on where you're sending this data, ultimately, where's the next hop. That makes sense? Okay, so there's the active routing that you have as a core network function. And then forwarding, move packets from the router's input to appropriate router output. Okay, so one of the things is it's going to figure out where should I send it, then it's going to actually send it. Okay, and then we can throw in the middle here, storing. So, as an alternate to packet switched networks, we can look at circuit switched networks. So, end-to-end resources allowed to reserve for call between source and destination. So, think of these like the telephone network. And if you go back historically, you know, you've seen them probably in the movies where the person picks up the phone and, you know, they just lift it to their ear and there's like a human being on the other end. It says, "Who can I connect you with?" And you're like, "Give me to Bob on his farm," right? And then they patch them through, okay? They're completing a circuit. So they're formally making a circuit from source to destination, and that is a dedicated circuit, a dedicated connection between those two places. All right? So instead of you having to go through each of these machines and these machines making real-time decisions, the circuit connection is pre-established for you to send stuff. All right? So we have links between, so think of these as like 4 different routers. Okay, these are 4 different routers, and each of them is connected to each other. Let's see. Okay. Basically, I already explained all this stuff, just I think way better than this. This is stupid. So in any case, we want to send stuff to this guy. We want to make a call to Bob's farm, and we're over here. The probably the person in the middle here would be the best example for our telephone network operator. So Bob's farm is connected to the telephone operator. We are connected to the telephone operator. Bob, so that when we pick up the phone, the telephone operator connects the wire between us and Bob's farm. And now we have a direct circuit connection. That makes sense? Okay, so now, on top of all of these, and this, well, This is specifically for circuit switch, it's saying here, but this could go for packet switching as well. These deal with multiplexing. So FDM is frequency division multiplexing. TDM is time division multiplexing. Go ahead.
Multiplexing anything like multi-threading?
It is not.
You were so hopeful.
Okay. The concept of multiplexing. This would be a good quiz question at some point, maybe. Multiplexing is taking multiple network signals and compacting them along a single channel. So a good example of this might be, let's say that you have a single, and where multiplexing is most commonly used on larger networks is, let's say that you have a large university campus, bigger than Concordia here, where Concordia is basically one giant building. But let's take a more traditional university campus where you might have buildings spread across several blocks, right? Several city blocks. And let's say that going diagonally across campus, you have buried a piece of fiber optic cable. Okay? And the job of that fiber optic cable is to link one portion of the network to another portion of the network. Okay? Because these guys aren't sitting right next to each other. You're not running Ethernet cables. All right? Now, so we're on one part of the network, and they're on another part of the network. And each of those individual parts of the network might have, let's just say, 200 cables, 200 Ethernet cables that need to be connected. Okay, so we have two options. We can run 200 really long Ethernet cables, Cat5 cables, across campus, several city blocks. And then if we ever need to add one more, what do we need to do? Dig up the ground again, rebury one more network cable? Maybe we'd be a little more efficient and bury them in strands of 10. You need to add one, we'll add 10, right? Okay. Instead, what we do is we bury the fiber optic cable once, which gives us a maximum bandwidth between one end of the campus and the other. And then we put pieces of equipment on either end of that called multiplexers. Okay? And the multiplexers allow us to take those 200 cables and turn it into a single data stream. The multiplexer on the other end takes that single data stream and splits it back into the 200 cables. Make sense? That's what a multiplexer is for, a multiplexer and a demultiplexer. Okay, so that's what multiplexing is in general. Well, this is frequency division versus time division multiplexing. That is, how do we have multiple things traveling over a circuit switched network? So on one hand, we can send the different, in using your example of those 200 signals, 200 wires, we can send the signals from one of the wires for some fraction of a second, followed by another wire for a fraction of a second, followed by another wire for a fraction of a second, all the way till you get to wire 200, then go back and do it again. So each wire gets a little bit of time for it to send data before the next wires turn. The alternative is frequency division multiplexing, which allows us to send everything at once, but each one is allotted a very small piece of the total bandwidth. So instead of it having to wait for an amount of time, it's only getting to use kind of a slower lane of traffic. That makes sense? For sending stuff. That's probably the best way of putting it. So if we look at the frequency, notice everything, in this case, instead of 400, we have 4. Or 200 in my example, we have 4. So all 4 things are able to send at the same time. In time division, they're alternating back and forth between the 4. Does one seem better or worse than the other? Given the example I gave you a minute ago about connecting 2 networks across a campus, obviously they both exist. So does one seem better than another?
The time division seems to be more equal for everyone, rather than by luck. I don't know. Who in the frequency who receives who is the first will have complete the pack.
Isn't it the other way around? This is frequency. So isn't frequency more even for everybody? Everybody's traveling at the same speed. If you have 100 megabits of speed and you have 4 guys, each one's getting 25 megabits of bandwidth. It's equal, right? Here, each of these guys, when it's their turn to transmit, gets the full 100 megabits of bandwidth. Make sense? Okay, so what kinds of problems does this lend itself to as being, you know, as being more ideal, versus what kinds of problems does this lend itself to being more ideal? I guess you could look at it from another thing is, what kind of data would we be dealing with up here, and what kind of data would we be dealing with down here? Go ahead.
Kind of the same thing with like serial versus parallel.
Exactly the same thing as serial versus parallel. Okay, so which of these is serial?
The bottom one is serial and the top is parallel.
What's the difference in serial and parallel?
Serial sends it in bits.
One bit at a time, one after another,
Yeah,
linearly.
so that's the bottom one.
You think this is the bottom one?
Because wouldn't it alternate in between each one, little tiny chunks?
Nope, serial's one after another in a linear line. This guy's going to send your data in a constant stream, one bit after another, along the channel it was given. This one down here is going to be bursty. You're getting a data chunk, then you get another data chunk, then you get another data chunk, then you get another data chunk, with an emphasis on chunk. That word's fun to say. And so this is going to be more like your parallel, where things are sent bursty, so like USB type technology. We go back to hard drive, talking about hard drives. USB hard drives might have a faster top speed, but it tends to be bursty. Where serial FireWire hard drives, for example, might have a slower top speed, but the speed of it's much more consistent. So up here we have a very consistent speed. And depending on how many things you're trying to multiplex, potentially a very slow speed, but at least it's predictable, right? It's a predictable speed. This guy down here may not necessarily be predictable. Why? Well, let's just say this is just to keep this in human terms, this is a 10-second window that each of these guys gets to transmit data. And they have a total of 100 megabits of bandwidth in our example here. Well, let's say that they're just sending a relatively small file. They're going to use a very small percentage of their total bandwidth for a very small percentage of their total time. In effect, wasting bandwidth that could have been used by some of these other ones. Does that make sense? Okay, but if they have a lot of data that you need to send out, let's say you're transmitting a 10 gigabyte file. Well, if you have a 10 gigabyte file, you could fill a 100 megabit pipe for 10 solid seconds, couldn't you? Now you're getting full use of that pipe. And then at the end of your 10 seconds, you're cut off until it's your turn in line again to send another burst of data. Kind of make sense? So each of these has a merit, but based on its own, based on different types of data. For instance, if you were streaming Netflix, which of these would you prefer to have?
Depends on the quality I'm streaming.
Oh, I don't think it does.
No? You want one with the highest bandwidth.
But
Is it FDM?
yeah, FDM. Who cares about the highest bandwidth is? We'll buffer until we get up to what we need, right? So, this might take a little longer to buffer, but once we have it buffered to the point where we can rely on whatever this network connection is between us and Netflix, if that's where the multiplexing is happening, is that's the source and destination. Once we've matched up that speed, we can rely on it being consistent. If you're a Netflix watcher, nothing ticks you off as much as sitting there watching a movie and it constantly pauses. Then it's rebuffering, then you're good for 3 or 4 minutes and it pauses, right? That's infuriating. You would rather, rarely is this going to happen, but you would rather wait 5 minutes up front for it to buffer and then be good to go for 2 hours, right? We might not enjoy that 5 minutes, but if we had the experience, we'd probably just assume something was wrong if it was taking 5 minutes. But if we had the experience that a 5-minute buffer would eventually end and then we were good to go, most of us would wait that 5 minutes, knowing that, hey, I'm not going to have a problem the rest of the time. As opposed to if it just instantly starts playing and 10 minutes in, you're waiting 2 minutes. Something like that, or it crashes because the buffer messes up or something like that. Okay, so we understand the difference between these. Okay, this is the means by which we can send multiple things over a network. In this case, we're talking about generic networks at the same time. How does data go at the same time? Send them in time-divided chunks or frequency-divided chunks. Frequency being different amounts of bandwidth. All right, so packet switching versus circuit switching. Which do you think is better? And, well, they both exist. So what types of problems does a packet switch network lend itself to? Try not to read this slide too much. Here, I'll kick it up so you don't read the slide too much.
Well, packet switching, wouldn't it be like more traffic on the highway and possibility more collisions rather than like FTM where it's just everybody's divided up? It'll be slower, but you get the consistent, or you get reliability.
Well, understand FDM and TDM have nothing to do with whether it's packet or circuit switched. Those are, any sort of network can be FDM or TDM. Typically, packet switch networks are TDM, but they could be either. It doesn't matter. So for right now, we just assume they're either one. I'm talking at the high level, circuit switch versus packet switched. What kinds of problems lend themselves to packet switch networks? When you sit down at the computer and you go to a web browser, and you type in www.google.com and press enter, is a dedicated circuit between you and Google being established? Or are you just sending this request out there on the global internet network and hoping for the best? Okay? Why? Why don't they just establish a direct connection with you at that point in time?
A lot of other people to do.
A lot of users. A lot of users. If they're going to have to go through the process of essentially hard coding a circuit between the computer you're on all the way to Google's server, for every single user who's trying to hit Google every single time, that's a performance hit, right? Instead, what do? They just let you dump your request on the internet, and we rely on some sort of back-end protocol to guarantee, whatever that means, it gets there. Okay? If it doesn't eventually get there, it just keeps resending. So potentially it can, in perpetuity, continue to resend your request. But we can trust that it's doing that, doing that on our behalf. Okay? So in any case, a packet switch network lends itself to networks we're commonly dealing with. Internet. Makes perfect sense for a packet switch network. What about circuit switch networks? Well, they gave one example here of the telephone network, right? So when you make a phone call, you hear you hear it ringing, right? Okay, when it's ringing, usually when you dial the number and then you start listening, is there a pause before you? I mean, like, you don't just dial a number and you're instantly hearing this person say hello. Although, has that ever happened? Mm-hmm. It's like freaky, right? Like,
Were you holding the phone?
It actually happened to me one time. It was years ago with not a super early cell phone, but an earlier cell phone when flip phones were cool. I was in the car and I was singing one of the, I don't like a lot of music, but one of the songs I like is Living on a Prayer by Bon Jovi. So I'm like screaming it into this headset because I just got off the phone with my wife. And this was back when we were still dating. So this had to be 16, 17 years ago, something like that. And all of a sudden, there's somebody in this earpiece. This is when they were plugged in. This is way before Bluetooth. It's like, shut up! Will you shut? I did not make a phone call. But somewhere, something zigged when it should have zagged. And the circuit was... So, I was serenading them. I was serenading somebody. So that was pretty funny. But in any case, typically when we make a phone call, we dial the number, we just hit the person's picture, right? Anymore, we just
I just
tap their face, it goes, or tell Siri to do it, whatever. And then there's a little delay, and then all of a sudden you hear it ringing. When they pick up, that establishes the circuit, correct? That establishes the circuit connection between you and them. Okay, good enough. Now, with that technology actually gets more complex when we're dealing with cell towers. If you are dealing with landlines, circuits make tons of sense. When you're dealing with cell towers, now you're jumping from tower to tower to tower. Now you're trying to maintain that circuit, but it's a moving target. See, your starting point used to be on this tower, but now you're here. Now you're here. Now you're here. So you're having to pass that starting point off a bunch of times. So it starts becoming a little bit more of a hybrid network at some point. But certainly, if you are only making connection with a single endpoint, and we're not dealing with, wouldn't you agree that there are far less people making phone calls per second than there are people making Google requests per second? Yeah, I mean, there's still a lot of people making phone calls, but a lot less than are making Google search requests. Make sense? So that would be the type of problem on the smaller scale that might start lending itself to a circuit switch network. Reality today, our cell networks are somewhat of a hybrid. A lot of them start using some voice over IP stuff that takes advantage of the benefits of packet switching while still acting like a voice network. Yeah.
Would something like Skype be circuit switching?
Probably not, would be my guess. I don't know what how their protocol works, but it goes over IP, so it uses Internet Protocol, which by definition is going to be a packet switch network. I suppose it's possible that their technology has because they write the client, that the client establishes a direct connection with the Skype server, and then the Skype server forms the circuit between the two endpoints. But since you're still flowing through packet switched routers and switches, at some point in there, it's packet switched. So in that particular case, Skype doesn't really get to make the call, I guess is the thing. Okay, so punchline here is circuit switching makes more sense with fewer users. Packet switching makes more sense with more users. Okay, so if you have a bunch of machinery that have to work together, maybe it's at a factory or something like that, they might be connected together in a circuit switch network because it's less about making lots and lots of people happy. It's more about keep maintaining communication links between several endpoints at a consistent rate. That makes sense? They each kind of have their perks. So it's not that one is better or worse than the other. In almost every example of computer science, the weak point is the people. We want everybody to make us happy. And we like things to be really fast. We don't like disconnects. We don't like sharing. People suck is what it comes down to. All right, so we'll stop there. There might be a quiz next class. We'll see. We'll see, maybe. Maybe. I reserve the right to give a quiz.
I'll shoot you a text later and talk more about me missing like 10 days.
All right.
But I should